Passenger of mass 5 meters is on a Carnival Ferris wheel, which moves at a constant speed in a circle. What is the force the passenger seat will exert on the passenger at the top and the bottom of the motion? To start, let's draw a free body diagram at both points. First, we can look at the sketch. Draw our radius of 1 meter and the guy at the top with the velocity of 5 meters per second to the right. And then at the bottom, his velocity is going to be 5 meters per second in the opposite direction to the left. And ARAD's always going to be pointing towards the center because this is circular motion. It's also given by v squared over r. This is our acceleration equation for circular motion. So we can draw our free body diagram at the top. This is going to be the norm force at the top. This is going to represent the force that the seat exerts on the passenger. We also have the weight force. We have the acceleration radial going down at the top. At the bottom, we have the normal force. We're going to label it NB. This is the normal at the bottom. And then we also have the weight force. But ARAD's going to be pointing up in this direction. And I just want to note, ARAD is in opposite directions at each point. This is going to affect our calculations later. So we can draw a coordinate system and apply Newton's second law in the y direction. Start by looking at the top. If we look at our sum of forces at the top, we have the normal force, the weight force, and we have ARAD going down. So we plug all these in, and ARAD's negative. Because of our defined coordinate system, we defined up as positive and it's pointing downwards. So we can replace ARAD by v squared over r and weight by mg, and it gives us this expression here. And then we can bring mg to the other side to isolate for the normal force. Plug in our parameters given by the question to give these two terms here, and then we can evaluate these terms, the amplitudes in the units. And if we do that, we get this expression here. Let's do a simple addition and get this for the normal force at the top. I just want to note the normal force is pointing downward. This is a key aspect of the motion, and I'll explain why that is later. So if we look at our sum of forces at the bottom, we still have the normal and the weight, but we have ARAD pointing up. So ARAD's going to be positive. So we can plug in ARAD equal to v squared over r and weight equals to mg, and then bring weight to the other side. Plug in our values given by the question, just like before. And then if we evaluate the amplitude in the units, we get this, and then just add them together, and we get this for the final answer. So this is going to be the normal force felt at the bottom. If we look at our diagram here, at the top, our normal force pointing downwards is going to be 76 newtons. And then at the bottom, our normal force pointing upwards is going to be 170 newtons. Notice that they're not the same value at each point. This is crucial. And the normal force is pointing down at the top because the normal force represents the force of the surface pushing inward, which is the direction of the centripetal force required for the object to travel under circular motion. So this makes sense. Also remember, our summation of force has to be in the same direction as ARAD in uniform circular motion. This is fundamental from Newton's second law. So that's why this makes sense.